Hey everybody, Fred here, PLCGurus.NET. Thanks for tuning in. Okay, so in this video, I want to divert a little bit away from PLCs and controls and networking, and I want to dive into some more electrical theory, and really not heavy theory, but I think it's good maybe to touch on, particularly for those electricians out there who are very strong at code and installation, and even those technologists, engineers who want a review on practical electrical systems, where these, rules come from to some extent, how we can dive in and get deeper insight into circuits, particularly those circuits that we're installing in the field, like single phase, three-phase type circuits, how to calculate neutral currents, how to do these things. So we're going to start right at the basics here. I'm going to talk about resistivity of a conductor, where the current carrying capacity of a conductor comes from, and then maybe dive into single phase 2-wire, single phase 3-wire systems, and really start to analyze these circuits from a practical application and installation standpoint. We're going to start the basics. Let's look at where the current carrying capacity of a conductor really comes from. I know we have tables that cover that, but let's dive in a little deeper. So get your pen, get your paper out. We're going to do a little bit of math, not too crazy, and I'll do my best to explain things as we go. But like I said, I am assuming you have a little bit of electrical background. So if you don't, you might get a little lost. But again, for those technicians, technologists, electricians, engineers, no problem. Let's do a nice review of these systems, and let's get started. Okay, so I do want to say, if you are new to the channel, please do consider subscribing, smashing that notification bell so you know when I'm dropping new videos, and giving me a thumbs up if you learned something in this video. Okay, so I'm going to head on over to my whiteboard here, and I'm just getting used to this. I got this digital pen, so bear with me. I hope you can make out my handwriting a little bit. And we're going to talk today about the current carrying capacity of a conductor. And we have all these tables. In the CEC, I'm from Canada, so you have your tables 1 through 4 that give us all the different conductor sizes in one column, and then depending on the temperature of the conductor's insulation, the different ampacities or current carrying capacity of that conductor. But where are these tables really derived from? Well, it's important, or where these things come from, there's a relationship between the cross-sectional area of a conductor size of a given metal type, copper or aluminum, at a given temperature. And this is known as the resistivity of the conductor or copper at a given temperature. And so very simply, let me just pull up my pen here just to give you an equation. The resistance of a conductor is equal to the resistivity of that conductor. Now this is not P, this is something known as rho. It's a Greek letter rho, and it is the resistivity of a conductor, and the length of that conductor divided by something known as the circular mill area. Okay, now let's talk a little bit about circular mill area, and I got a couple of notes I'm going to do for you so you understand what this is. And so this is, and let's just make a note here, this is the resistance of conductors equation. Okay, and I'm assuming you know what a conductor is. It's basically a wire equation. So we'll just say equation. Okay, now let's talk about the CMA for a little bit here. Okay, and I have some formal definitions here, so it's very clear what the CMA or circular mill area is. Okay, so this is the, let me make a note, this is the circular, I'm going to spell this wrong, circular mill area of the conductor. Okay, and again, like I said, I want to dive into some of the math behind, and then we're going to build out and start analyzing practical circuits that, as an electrician, you're installing every day, but just to give you some more insight into these circuits. But we're going to start here, okay? All right, so let me go back to let's make a note. So the diameter of a wire, I'm going to make a little note here, a little bullet point. A diameter, I got my little cheat sheet over here, of a wire is measured in mils. Okay? In mils. So we're dealing with the SI units here, right? But let's talk about that. So a mil, let's just define a mil now. A mil is defined, just for our American counterparts, as 1,000th of an inch. Okay. And let's just do this, 0.001 inches. Okay? All right, so we have a definition for a mil. Now, that's for the diameter of a wire. So a circular mill is the area of a circle that is 1 mil in diameter. Okay? Stay with me. Is 1 mil in diameter. Okay. I'm just going to move this up a little bit. All right, so just so we don't lose track of anything, I'm going to try to do this as best I can, guys. All right. So we often say, and you'll see in a lot of books or online, that they often equate the circular mill area, let's do this, the CMA of a wire determines the current carrying capacity of the wire. Carrying capacity. Okay, we got some notes here, right? We'll do some examples though of a wire, but I want to make sure we have a good definition. Okay, good. And they often say, like I said, I was going to talk about earlier, they often say the CMA is proportional, we'll say it's proportional, approximately equal to the diameter of the wire squared, okay? And, you know, I found myself scratching my head, okay, how does the area equate or is approximately equal to the diameter squared of the wire? Well, then I started thinking about the area of a circle. So what is the area of a circle? Well, if we want the area of a circle, we'll say, that is defined mathematically as pi r squared. Okay, right? This is back to high school mathematics or college mathematics, right? And so, well, now if we start to break that up a little bit, what does that really mean? Well, it's the pi, and what is the radius? Is the diameter of a circle divided by 2. So we could rewrite this as diameter over 2, and of course it's radius squared, so we'd have to do that twice, right? Diameter over 2. And then we could rewrite this as pi d squared over 4, right? And so hopefully you're with me on this, but if we look at what is pi, well, pi is approximately, 3.14, blah, 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 blah. And I think what they're doing, they're to keep it simple, is just say, well, it's not quite 4, it's almost 4. And so this almost cancels out. Whoops, let me undo that. Almost cancels out, right? And so to simplify it, you'll see written in textbooks and these other things that the circular area is approximately equal to the diameter of the conductor squared. And I think this is where it comes from, because if you break out the area of a circle and write it in a different form, you can see where it almost cancels. Okay, so I think we have a pretty concrete definition of what a mill is, what a circular mill is, and what the circular mill area of a conductor is. So I think at this point I'm going to bring in a couple of things to explain this a little bit further. And these are things I just found, images I found online in a text. But let me see, I can add an image. I'm going to add a couple of images because, I mean, we need to know what the circular mill area is of certain conductors. And let me, oh, that's pretty small. Let me see if I can make that bigger. Oh yeah, we can make that bigger. Let me move this up here. And so, again, I just kind of found this image online, and I'm just going to block it over here just so we can see it for a second. But you can see the standard conductor sizes that you're going to see in your code book, okay? You know, number 14 right through to a 4-aught conductor. And you can see here the circular mill area, or CMA, of those conductors at a given size, okay? And again, this is not something you're going to remember, guys. This is why we have code books with tables. All this is already done. Again, this is just providing some deeper insight into where these things might be coming from, okay? So let me shrink that a little bit. And actually, let me move this up here. So remember, before I do that, let's just review here. Remember, our resistance of a conductor equation is equal to the resistivity of the conductor, which we haven't talked about too much yet, which is the Greek letter rho. It's not a P, it's the Greek letter rho, multiplied by the length of that conductor, divided by the circular mill area of that conductor. Okay, great. I think we're doing it some justice now. All right, so we have our common conductor sizes and their equivalent circular mill areas right here. Now I'm going to go ahead and add one more image here because we need a little more information. And again, this is largely academic, guys. We're going to get into some more interesting things in the next video where we look at actual circuits and how we can extrapolate or analyze and pull out information that, you know, more information than maybe just, okay, what size conductor do I need to run on a 15 amp circuit? All right. I mean, well, let's look at maybe a little more, like what is the voltage drop across that conductor? You know, what am I going to measure at the load versus at the supply? You know, what's the efficiency of that circuit? And these types of things. So that's where we're going, guys. So please stay with me. It's going to get interesting. And then we're going to build on that example and how do we calculate things like neutral currents. This is something that really eludes a lot of people on when you talk neutral conductor sizing and how to actually calculate the unbalanced load flowing on a neutral conductor. So again, we're going to get there. Stay with me, guys. But for now, let's talk about resistivity. And you can see here, I have a table, again, I found it online, that gives the resistivity of copper and aluminum at certain temperatures. So you can see here, the resistivity of copper at 20 degrees C is 10.4 ohms, and this is a pretty odd unit of measure, circular mills per foot, okay? So it's 12 ohms at 60 degrees C. So you can see as the temperature increases, so does the resistivity of that conductor. So you have a direct correlation there, right? So you can see the different ones here at 75 degrees C, it increases a little bit more. And you can see as we get into higher temperatures, it's just going to keep increasing in that way, okay? And so now I think if we know the resistivity of the conductor, of the metal that we're using, and we know the circular mill area of the conductor, then we can begin to calculate things like the resistance of the conductor, the voltage drop on a conductor, and these types of things. So I'm going to maybe give you one more equation here, and that is for voltage drop. And then maybe we'll come back and we'll do a quick little example. And I think we're going to be done with this video because I want to get into actual, panel distributions, branch circuit distributions, and do some calculations on them. But I thought this would be a nice little precursor to that. Okay, so if we ever wanted to calculate the voltage drop, we have a relationship or a formula for that. Again, it's the resistivity of that conductor multiplied by the current, okay? Multiplied by the length, multiplied by 2, because remember, on a circuit, we go out to the load and we come back to the load. And so that's why we're multiplying it by 2, and then you're going to divide that by the CMA. Okay? Now, I wrote it this way because this is the way you see it written a lot, but I'm going to rearrange this a little bit. So let's rewrite it like this. So I'm going to rewrite it as the resistivity multiplied by the length multiplied by the current, and then we'll just multiply it by 2. We're just multiplying by 2. And I want to write it this way for a particular reason, because, over the CMA, because I want you to look at this part right here. Okay? What is that? Well, we just defined what that is above, didn't we? Let's go up here, and the resistivity times the length over CMA is our definition for the resistance of a conductor, right? And so really, what is that? That's just resistance. So we could even rewrite this one more time as the resistance times the current times 2. And remember Ohm's law. What is Ohm's law? Let's just draw it. It's volts. Let's do the triangle. The Ohm's law triangle. Remember this, guys? Let's do it like this. Is your I times R, right? Which is exactly what we would expect it to be right here. But we're just defining it in more, I guess, granular terms when we start talking about resistivity of metals, the effective length of conductors, the cross-sectional area, the circular mill area of a conductor. You know, this is really where the resistance comes from in the standard equations that we see for voltage. All right? And so I thought that's an interesting correlation or way to look at things. And what we're going to do, why don't we do this? I have a little example prepared, and why don't we solve it in terms of resistivity and circular mill area, and then, you know, maybe in future videos we're going to use the Wireman's method or the code way to solve circuits. But I thought this was an interesting thing to kind of show you. It's a good review, provides deeper insight. So let's do a quick example, and then I think we'll call it a wrap for this video. Okay, so let me slide this up a little bit. And actually, you know what we might do? I might actually move these down because I think we're going to need them for our little examples here. Move this up. And we'll keep the Ohm's law triangle there because we're probably going to need that too. And let's get my pen back out here. And I'm just going to type in, or I'm going to write down the example here. So example 1, what is, and I've got it written over here, what is the maximum one-way distance? So we're getting into a little more practical installation now. Distance that a number 10, whoops, let me undo that. A number 10 2, so 2 conductor. And we'll say, you know, I don't know, let's just say NMS 90, so we'll say an NMSC cable, so a non-metallic sheath cable, 90 degrees, copper wire circuit, may be run from the panel, so we're talking about from the distribution panel, we'll say the distribution panel, if it is carrying a load of 18 amps at 240 volts with a maximum allowable voltage drop of 3%. Okay, so there's quite a bit to unpack in here, isn't there? So I'm just going to slide this up a little bit. I don't want our little diagrams to come out. I mean, we have Ohm's law. Well, we can maybe we'll just move these down one more time, just so we have them in view. Okay, let's do that. That's good. So what is the maximum one-way distance that a number 10 to conductor NMS90 copper wire circuit? Well, that's okay. That's kind of confusing there. Let's just get rid of let's get rid of the conductor here. We don't need that in there. That a number 10 to NMS90 copper wire circuit may be run from the distribution panel if it's carrying a load of 18 amps at 240 volt with a maximum allowable voltage drop of 3%. Okay, so quite a bit to unpack here. So I would first calculate, okay, what's the maximum voltage drop, or maybe before we do that, what's the resistance or the maximum allowable resistance of the conductors at this point, right? Because we can only tolerate a 3% voltage drop at the load. And so let's make a note here. So we'll say the maximum, so we're calculating the wire resistance essentially to see how much voltage drop, or to set the maximum allowable voltage drop across the wire. Okay, so the max wire run resistance, let's just make a note here, resistance, and this is just going to be an Ohm's law type thing, and we can say R equals the V over I, right? That's just our Ohm's law. Let's draw our little triangle right here again. We got V, I, R, right? All right, there's our little triangle. There we go. Good, just so we have Ohm's law handy. There we go. Good. And here we're given it's 240 volts. 240 volts over our load current of 18 amps. But we need to multiply that by 3%, right? So multiply that by 0.03. And if we punch that into a calculator, I ended up with 0.4 ohms. Okay, so our maximum wire run resistance is 0.4 ohms. Okay, so that's how we're going to stay inside of that 3% voltage drop, right? Because the voltage drop, the conductors are going to contribute to voltage drop, right? All right, let me move this up a little bit. Hopefully that's clear. And now let's recall that our formula for resistance, so we'll just say recall, and this is what we looked at above. I'm just going to rewrite it here so we have it. Resistance of a conductor is equal to the resistivity of that conductor multiplied by the length divided by the circular mill area of that conductor. And so if we transpose that equation for length, transpose for length, transpose for length, for L, we can see that therefore L, now let's do this, equals, so we want to isolate the length here, so it's going to be R times the CMA over the resistivity. Okay? And now what do we have to do? Well, we have to go, we have the resistance, we just solved for it right here, right? So there's our resistance of our conductor, so we can plug that right in. So we have 0.4 ohms. But now we need to multiply that by the circular mill area of the conductor, and we're told in the question up here that it's a number 10 conductor, right? And so a number 10 has a circular mill area of 10,380 circular mills, and so we can just go ahead and plug that in. Let me get my pen handy. So we have 10,380 circular mills. Okay, and we just divide that now by the resistivity, and we're told it's copper, and we'll use the resistivity of copper at 90 degrees C. So we're just going to assume it's at 90 degrees C, and again, so we have 13.2, I'm just reading that right here at 90 degrees C, 13.2, and that goofy unit, circular mills per foot, and that's going to, things are going to cancel out here, right? And we're going to be left with feet, right? And that's what we want. We want to know how long we can run this wire. And once you plug all of that into your calculator, you're going to get to an answer of What's the answer here? 300, I just did it over here, 314.55 feet. Okay, so this is the total wire run resistance. This is the max wire run resistance. This is the total wire run. So that's to the load. That's to the load. We'll just say to the load and back, right, to the source. So we want the one-way distance. Where did it say that? The maximum one-way distance. So what do we need to do here? We want the maximum one-way distance. Well, we're just going to take that and divide it by 2, and that's going to equal 157, if I punched it in my calculator correctly, 0.27 feet. Okay? And so we know that we, under this condition at 90 degrees C, an 18 amp, something that's drawing 18 amps at 240 volts, we're running a number 10 copper conductor. We can run that conductor 157 feet, but of course there's many other things we have to consider here that these equations aren't going to factor in, like termination rating of conductors and these types of things, or termination rating of devices, all that good stuff that we need to be cognizant of as well. But from a purely engineering perspective, we can answer it this way, right? Okay, that's not bad. That's not bad. Let's do one more example. Let's just try a different one. I'm going to just move this up, and hopefully you're finding this somewhat interesting. I think it's interesting anyways. All right, so we'll go example 2, and I think this will be the last one. Let me write it down. Let's take a look at this one. It's a little bit different. I have another one here, and I got some of these right off online. People are asking in forums and things. So a branch circuit, it's probably somebody's homework, right? I think it was on Reddit. Branch circuit supplies a resistive heating load. Resistive heating load, okay, that makes sense. Of 10 amps. Okay, good. I think we're going to model this one in our next video. We'll just draw the circuit out. The distance from the panel to the heater is 35 meters. Okay, meters. Calculate the voltage drop using number 10 AWG copper, given its CMA of 10,300, well, just straight from the table, circular mils, and resistivity is, okay, so this is right from the little images, but that's okay. 12 ohms, circular mils per foot at 60 degrees C. Okay, so we don't really need our little tables up there for this one, do we? That's all right. We could have gotten a lot less in this question for sure. All right, so a branch circuit supplies a resistive heating load of 10 amps. The distance from the panel to the heater is 35 meters. Calculate the voltage drop using a number 10, given its CMA of 10,380 circular mils, and resistivity is 12 ohms circular mils per foot at 60 degrees C. Okay, so what I would probably do is I would break this up, break this up into two problems, or break this up into two problems. Okay, and so one, and what did I do here? So we find the resistance equals, again, we're just back to our equation, but we're going to multiply by 2 because we're going there and back. divided by the CMA. Okay, and then we're just plugging in the numbers essentially here. So the 12 ohms, circular mils per foot. But now we got to be careful here. Also, this is the little kicker with this one, is this one's actually given in meters, right? And our units are feet. So you always got to be mindful of units, guys. So you want to convert your meters into feet. And so we're going to do that by multiplying the 35 meters times 3.28 feet per meter. And of course the meters are going to cancel. We'll multiply that by 2 and divide that by the circular mil area, which again is pretty much given in this question, 380 circular mils. Okay, and then when you plug all of that good stuff into your calculator, you're going to get a resistance of 0.265 ohms. And then you can just go ahead and solve for voltage drop. So we'll just solve. Now that we have that equation, it's just simple, or we have the resistance of the conductor, we can solve for voltage drop on the circuit. And so if we were to put a meter right across the load, of course, if we're supplying the, what is it? Is it 120 volts? I guess it doesn't really, I guess it doesn't really say, it doesn't really matter. We're just going to multiply what the voltage drop across the conductor is. So we're going to solve for voltage drop. V drop, we'll call it. And that equals our I times R. And we just solved R, and we know our load current is 10 amps. Because we know the current, we can just multiply it by this. And when you plug that in, you're going to get a voltage drop of 2.65 volts. Okay? So you can see here, I mean, at the end of the day, are you ever going to do this in the field? Probably not. But I think it's important that you understand maybe, you know, where some of these things in the code book are stemming from. You know, how, you know, a little more insight into the properties of metals, you know, resistivity, how we can account for things like voltage drop, how far we can run a conductor of a given size, of a given resistance, of a given load. So all of these things are important, and at the end of the day, I mean, yeah, can you go to the code book? Okay, 15 amps, I'm going to, you know, use this conductor, and you know what, I'm not going to think about it. If I'm running it a long way, I'm just going to upsize it 1 conductor or 2 conductors, and I know I'm going to be good for voltage drop. I mean, that's fine, but sometimes it's nice and it's fun just to think about it more and understand where this stuff is coming from and how you can actually mathematically calculate some of these things. So again, I think I'm going to leave it at this. I mean, these are just exercises in doing, I guess, engineering math. However, in the next couple of videos at least, I want to get into how to analyze, say, a circuit like this, where you have a single phase 2-wire circuit feeding a load like this. You have a given resistance of the conductors, you know, how, you know, the power being consumed by that load, the power being supplied by the AC line, how you can calculate the unbalanced load currents traveling on a neutral conductor in a 3-wire system. So similar to, you know, what electricians are installing every day in residential, commercial installations. I mean, the neutral current one is one that eludes many people, and it's because you have to consider more advanced math in terms of things like power factor and, you know, impedance phase angles. And I'm not going to get too heavy into it, but we're going to cover enough so at least you understand, you know, how you can calculate something like a neutral current on a, say, a single phase 3-wire Edison type transformer installation. So this is Fred. I hope you enjoyed this video. It's a little bit long, it is, but you know what? If you're into this stuff, if you're learning this stuff, if you want a refresher on this stuff, you know, it's kind of fun just to come along with me for the ride here. So I thank you for tuning in. Please leave comments in the comment section. Please subscribe to the channel. Please head on over to PLCGurus.NET if you haven't already done so. Become a member, you know, engage in our forums. Lots of very skilled, talented people are, constantly putting questions, answering questions. So if you're in the field of automation, controls, electrical, anything to do with that kind of stuff, PLCGurus.net is a great spot to come on over and join our community. So this is Fred. I thank you for watching. I'll see you in the next video. Thanks.